calculated enthalpy from stoichiometry, there's a couple other ways that we can do it. And the first is to use tables. It's often that the AP test will give you the heat of formation for certain compounds. And the heat of formation, or delta H sub F, is the amount of energy it takes to make 1 mole of a particular substance from its elements in their pure and standard state. And what do we mean by standard state? Well, we mean 25 degrees Celsius, 1 atmosphere, and if it's a solution or if it's a liquid, it's 1 molar. On the AP test, you'll typically be given this information in tables, like this one taken from your notes, where these are the heat of formations for 1 mole of each of these compounds. So 1 mole of water is negative 286 kilojoules per mole to produce it. And since these heats of formations are at standard conditions, or in their standard state, these compounds will also be in their standard state, meaning that water under these conditions is a liquid. Ammonia under these conditions is a gas. So let's say we have a chemical equation such as this. This is the combustion of octane to produce water and carbon dioxide. First off, this is not a balanced chemical equation, so let's make sure we balance this out. It would look like this once it's balanced. It would have 8 carbons on this side, 8 carbons on this side, 18 hydrogens. 9 times 2 is 18. That gives me 9 times 1 is 9. 9 plus 16 is 25 oxygens on this side. So I would need 25 divided by 2 oxygens over here. If I multiply the entire equation by 2, voila, I'll have a balanced chemical reaction. Alright. Now, given these tables, we can determine how much energy goes into forming each one of these reactants, or each one of these reactants and each one of these products. So let's put that in underneath here. Alright. So for every 1 mole of octane that's formed, it requires 269 kilojoules. Alright, so with these values, we can figure out how many kilojoules would go into the formation of, say, 18 moles of water or 2 moles of octane. So we're going to take these coefficients, we're going to take the coefficients of the balanced chemical reaction and multiply them by the heat of formation. Now these values, negative 269, negative 286, negative 394, came off of this table. But I bet you're wondering, where on earth did he get 0? Well, this heat of formation is the energy necessary to form 1 mole from the elements in their standard state. Oxygen is elemental. It requires no energy to form it into its elemental state, so therefore anything that's already an element, such as oxygen, or if you have a metal by itself like gold, its heat of formation is going to be 0. So this is why I've put 0 here, rather than look for a value on a table. Anytime you have a balanced chemical reaction, if you see an element, its heat of formation is going to be 0. So now let's multiply all of these values by the coefficients here to determine how much energy is necessary to form each one of these either reactants or products. So it takes 538 kilojoules to form 2 moles of octane, over 5,000 to form 18 moles of water, and over 6,000 to form 16 moles of carbon dioxide. Since this reaction is that we're forming these products over here, and we're using up these reactants, since the energy in the universe can be neither created nor destroyed, the change, or the delta H for this reaction, is going to be the change in your products minus your reactants. This is the basis of Hess's law. And your NIMSY notes call this the Big Mama equation because it's everything, the big picture of everything, of your products minus your reactants. So it's the heat of formation, the sum of all the heat of formations of our products minus the sum of all the heat of formations of our reactants will give us the change in the enthalpy for this reaction. So now we're just simply going to plug and chug. We're going to do this plus this minus this plus that. Once we set it up, simply plug it in the calculator and we find that delta H for this reaction is going to equal 10,914 kilojoules. Since enthalpy is a state function, it doesn't matter how we get to that value, it's only that we do. And if we're given multiple pathways to do it, we can come up with the change in enthalpy, or the delta H, for a particular reaction. So the AP exam will typically give us a couple of different pathways in which we can carry out the same reaction. This is actually kind of fun because you get to play with it and figure out which pathways can I possibly take to end up with the overall product in the end. So let's look at one of the sample problems. So if we're asked to find the overall delta H, or change in enthalpy, for this reaction, we're given a couple different pathways. You'll notice that none of them perfectly mirror this. However, there is one that starts with the reactant that we started with, and this is the second one down here. We start with H3BO3. That's what we're going to start with. That's what we're going to look for in the overall reaction. Now, there are a couple rules that go with this. So first, we're going to figure out, we're going to arrange the equations. We're going to arrange the equations in a way that gives us the overall product, this overall product that we are looking to get. And if we ever have to reverse a reaction, say we want to go backwards against the arrow, we're just going to flip the sign of delta H here. Alright, so first off, we've got this product here, we got this reactant here. It's seen up above, so let's start with that. H3BO3, let's copy this exactly as it appears. So we've got our reactant we start with, and it's going to give us these two products, which are not the products we were looking to get. I mean, one of them's there, but it's not the main goal. We're trying to get B2O3. We're going to get water along the way. So we need to get rid of this HBO2. We need to get rid of this HBO2, and we need to get to B2O3. So we need to end up making somehow whatever makes that. So we know that this is going to be our final. This third reaction down below is going to be our final product, or our final reaction, because that's going to give us a product. So let's copy that also. So we've got a reactants, we've got the products we're looking to get. We need to get rid of the things that are in between. We gotta get rid of the HBO2, we gotta get rid of this big honking compound. So we're gonna end up wanting, if the honking compound's on the reactant side, we're also gonna want it on the product side. So we're gonna want to produce this at some point. So if we do this reaction in the reverse, that will put this huge compound, this one up here. That'll put this huge compound as a product, and we'll do this huge compound as a reactant, and that will cancel the two out. So I'm going to take this, I'm going to put it in reverse. So now that I've reversed that reaction, you also see that I've flipped the sign because we're going in the opposite direction. In the forward direction, this had, up here. In the forward direction, this had a delta H, or a heat change in enthalpy, of negative 11.3 kilojoules. In the reverse reaction, it would have a delta H of a positive 11.3 kilojoules. Now I'm looking to end up with just 1 mole, right? In the balanced reaction, I have 1 mole of diboron trioxide, whatever that is. I have just 1 mole of that I'm trying to produce. However, if I look down here, I end up with 2 moles. So that's not going to work out. My coefficients are not equalizing out here. So I need to figure out some way in order to make this so that I would end up with only 1 mole of this. So right off the back, I can look at this one down here, and I'm only going to need to produce half as much as this is going to produce. So what I'm going to do is I'm going to cheat a little, and I'm going to put half a coefficient in front of each of these. So I'm going to take this reaction, and I'm going to divide it by 2. I'm also going to divide the enthalpy for that reaction by 2, because I'm only going through half of the reaction. So if I divide this by 2, this entire thing down here, when I do all of that, my coefficients become like that. Alright, and then if I look up here, now I've made a half of this, so I only need half of this large honking compound. I'm producing one of it, so I don't want that either. I'm going to need only a half of this actual reaction up here. So I'm going to take this whole thing and I'm going to divide that also by 2, which will put the 0.5 in front of each of those, and this 4 is going to become a 2. And I'm also going to half the enthalpy for that reaction. I've got 2 of these that I'm going to need. I'm only producing 1 from this first pathway that we used, so I'm going to double this first one so that we end up with 2. And now we can check our answer. If I add up all the products and add up all the add up all the products and add up all the reactants, I should cancel out and have this overall reaction. HBO2 on this side cancels HBO2 on that side. 0.5 H2B407 cancels H2B407 on this side. And then we can do some combining. We've got 0.5, we got 2 waters here, half a water and a half a water come to make another water, so that gives us 3 waters. Everything else just drags down, and look at that, we've got the exact same problem below as we do above. We can also sum up all of these delta H's because it's going to give us this overall product, so we can sum these up and we'll have our enthalpy for this reaction. The answer is 14.3 kilojoules. Another method for calculating enthalpy is if we are given the bond energy for particular elements or compounds that would form something. Since atoms are less stable or have more energy when they're on their own, they actually form bonds to become more stable. So they will give off energy to form a bond. But if you want to break them apart and return them to an element or ionic form, they actually require energy. We can use this knowledge to calculate the enthalpy for a reaction, because if we take the sum of the energies of anything that's broken and subtract from it anything that's formed, we'll come up with the enthalpy for a particular reaction. So let's see one of these problems in action. Here we have hydrogen and fluorine coming together to make hydrofluoric acid. We're given the bond energies for each one of these. So again, our formula is bond energies broken minus energies formed. So we can plug in here which bonds are going to be broken while hydrogen and fluorine are going to be broken. And hydrofluoric acid is going to form, so we can plug that in as well. Now it simply becomes a matter of plugging in the values for each one of these bonds. So once we do that, I almost made a huge mistake. Here I have a 1-to-1-to-1 ratio, right? Because this is 1, each one of these is per mole, which my units vanished for some reason. Hold on. There we go. So this is a this formula down here represents a 1-to-1 ratio. Well, yes, it would be great if I had 1 mole of hydrogen plus 1 mole of fluorine giving me 1 mole of hydrofluoric acid. However, I have a 1-to-1-to-2 ratio. So the bond energy here isn't forming just 1 mole of hydrofluoric acid, it's actually forming 2. So I'm going to have to take this value and double it. Now I can plug in the values. Once I do that, I find that the enthalpy for this reaction is negative 544 kilojoules. And that's the end of thermochemistry, or the first law of thermodynamics.